Greetings and welcome to the 14th episode of PHS Physics SOS. This is the first episode of the second semester, and I'm going to start by going over the first part of the Chapter 17 homework, which starts on page 654 with question 1. Question 1 reads, how are conductors different from insulators? Now, the simple answer is that conductors will allow a charge to pass through them, but insulators will not. But that's not really the whole answer. Really, conductors and insulators are on a spectrum of conductivity. And here you have things that aren't conductive, and here you have things that are conductive. And this is like not conductive at all, and this is like perfectly conductive. And over here you have insulators. So there's a range where, like, just because you say an insulator isn't conductive, well, technically it's conductive a very little bit, but depending on what the insulator is, it's either going to be conductive almost none at all, or maybe a tiny bit. And then you have semiconductors, which are, somewhat more conductive, and then you have conductors, and then you have superconductors. So the long answer is there's really a spectrum of conductivity, with insulators being the least conductive, superconductors being the most conductive, and semiconductors and conducors being in between. But basically, all you really need to know is that insulators don't conduct and conductors do conduct. Now the next question is question 2, which says, when a conductor is charged by induction, is the induced surface charge on the conductor the same or opposite the charge of the object inducing the surface charge? Now, the answer is opposite, because if you have, okay, so here's your conductor. You're charging it by induction, which means you have some other object, say a positively charged rod. If you hold this close, if you hold this positively charged rod close to your conductive material, it's going to induce a negative charge in this side of the material. But that means there's also still a positive charge on the other side of this material, because it started out with a net charge of 0 before you introduce this positively charged rod. And it has to end with a net charge of 0. So if you add up all these positive or negative charges, they're still going to be equal to 0, but there's an induced negative charge. But I guess the point of the question was they're opposite charges, because opposites attract. That's just a little more intuition that they're going to get into later in later problems. Now on to question 3, which says, a negatively charged balloon has a 3.5 microcoulomb of charge. How many excess electrons are on this balloon? Now this may seem like a weird problem, but really they're asking how many electron charges, and the charge of an electron is 1.6 times 10 to the negative 19th coulombs. So if you have a charge of 3.5 microcoulombs, or 3.5 times 10 to the negative 6 coulombs, how many electrons, which have a charge of 1.6 times 10 to the negative 19th coulombs, make up that charge? So all you do is you divide 3.5 times 10 to the negative 6th by 1.6 times 10 to the negative 19th, and you get 2.2 ignore that, times 10 to the 13th electrons. So that's your answer. That's how many electron charges, this value, are needed to make up that charge. The next question skips over question 4 and goes to question 5. It says, would life be different if an electron were positively charged and the proton were negatively charged? And the answer is no, because positive and negative are just arbitrary descriptions of particle behavior. I mean, we say that opposites attract and protons are positive and electrons are negative, but if we just swap those, opposites would still attract. It's just a name for the behavior we're seeing. But no, there really would be no difference. Next question is question 6, which says, if a suspended object is attracted to another object that is charged, can you conclude that the suspended object is charged? Now, again, I'm going to go back to our charged rod. So if you have a charged rod, we'll just say it's positively charged, could be negatively charged, and some object is suspended in the air, like those paper bits in the lab you did, they're asking, can you conclude that this object is charged? And the answer is no, because the object isn't so much charged as that it has an induced charge, or an induced surface charge, rather, meaning that there's just there's the negative. There's a negative charge on this part of the object, which is being attracted to your charged rod or charged object or whatever. But there's the opposite charge on this side of it. So ultimately, there's no net charge in it. If you add up all these negative charges on this side and all these positive charges on this side, it's still going to be equal to a net charge of 0. So no, it's not charged. It's just inducing a surface charge. The next question is question 7. And I'm going to warn you, this question is a bit weird. The question says, explain from an atomic viewpoint why charge is usually transferred by electrons. Now, the book says protons are relatively fixed in the nucleus, whereas electrons can be transferred from one atom to the other. But really, in my mind, that doesn't answer the question at all, because this is actually a really rather complicated question that covers things that haven't been taught and won't be taught this semester. But I'm going to go over them anyways because it's interesting. Really, electrons are easy to remove because the force that's holding them into the atom is not only a different force, but a much weaker force. If you have an atom, let's say helium, so you have 2 protons, 2 neutrons, and 2 electrons. Electrons are obviously much smaller. The force that's holding these protons and neutrons together is a different force from what's holding these electrons in orbit. The force that's holding the protons and neutrons together is called the strong nuclear force. And most of you have probably never heard of this because it probably hasn't, I don't think it's actually been taught in any classes. But it's one of the 4 fundamental forces, 2 of the others of which are gravity and electromagnetism. Electromagnetism is a lot of what we're talking about in this chapter with charges and stuff like that. And gravity, of course, we know about. But strong nuclear force is, well, as you can guess by the name, very strong. If we assign gravity a relative strength of 1, the strong nuclear force has a relative strength of, we'll call it G. And the strong nuclear force has a relative strength of 10 to the 38th. So it is 10 to the 38th strong, 10 to the 38th times stronger than gravity, but it acts on a very short distance. Gravity attracts every object in the universe to every other object in the universe, but it's very weak. This pen and this tape roll are attracted to each other by gravity. But because of friction and because of the air between them, they're not going to move towards each other, but they are attracted by gravity. So gravity has an infinite range, whereas the strong nuclear force has a relative range of 10 to the minus, actually it's not relative range, it's an actual range of 10 to the minus 15th meters, which is very, very, very small. So it's really only going to act within the nucleus of an atom, and it's what holds protons and neutrons together. Now, the force holding electrons to the atom is the electromagnetic force, which has a relative strength of 10 to the 36th. So it's still a ton stronger than gravity, but it's 100 times weaker than the strong nuclear force. But unlike the strong nuclear force, unlike gravity, it has an infinite range. So electromagnetic force and gravity act on an infinite range. Gravity is very weak. Electromagnetic force is very strong, and the strong nuclear force is even stronger, but it acts on a very short distance. So, back to the original question, which I'm going to reread because you've probably forgot it by now. I know I have. The question says, explain from an atomic viewpoint why charge is usually transferred by electrons. Now, the reason for this is because electrons are held to the nucleus by the electromagnetic force, and they're much further away from the nucleus. So not only is this 100 times weaker than the strong nuclear force, but it's acting on a much further distance. And the reason protons aren't transferred is because protons are held together in the atom by the strong nuclear force, which is almost impossible to break apart, especially by conventional means. So yeah, there's the answer to that question. And the last question, if you're not brain-fied yet, is number 10, which says, which effect proves more conclusively that an object is charged? Attraction to or repulsion from another object? Okay, so, oh, you can't see that 10. So, attraction to another object can be caused, well, okay, I'm going to give you the answer and then explain it. The answer is repulsion, because attraction can be caused by an induced charge, but repulsion cannot. And I'm going to draw a couple pictures to explain that. So if you have a charged rod, keep coming back to this example, but it's a good example, especially since you did a lab on it, and an uncharged object just has an evenly distributed charge, this rod is going to induce a negative charge in this side of the object and attract it to it, just like it did up here. So we'll end up with your charged rod and your object moving closer to the rod with an induced negative charge. So this doesn't prove that there's a charge in this object. In fact, there is not a charge in this object. So attraction can just be caused by an induced charge. Doesn't necessarily mean that there's actually a net charge in the object. Now, repulsion, on the other hand, can only be caused when you have two objects with the same charge. So if you have two positively charged rods, they're going to repel from each other. And this is never going to happen by an induced charge. This positively charged rod is never going to induce a positive charge on this side of it, because then it would repel. It wouldn't make any sense. It's only going to induce, well, as they say, opposites attract, so it's only going to induce the opposite charge so it can attract and be together. So yeah, back to answering the question, attraction does not prove net charge. Only repulsion is going to prove net charge, because attraction can be caused by an induced charge, but repulsion cannot. Alright, and that's about it. So thank you for watching this shorter episode of PHS Physics SOS. If you have any questions, leave them down in the comments below, or better yet, on the Facebook page, which will also be linked in the description down below. Or, yeah, get a hold of me on Skype or at school or whatever, and I'll do my best to help you. Thanks for watching.